In the heart of Cairo's National Center for Radiation Research and Technology, a remarkable story of innovation unfolds. Meet Salah Lotfy. A distinguished researcher from the Polymer Chemistry Department, Salah is a critical cog in the wheel of a team pushing the boundaries of material science. His unique expertise? Extracting chlorophyll from spinach leaves. Yes, you heard it right. The same vibrant green leaves that make Popeye strong are now being used to enhance the electrical performance of materials. By carefully treating these leaves with alcohol, Salah isolates the chlorophyll, a process that requires precision and a keen eye for detail. Once extracted, the chlorophyll is skillfully integrated into a polyvinyl alcohol solution, forming the foundation of innovative films. These films, when exposed to gamma rays, exhibit enhanced electrical properties. Salah Lotfy, a master in extracting the vibrant green essence of nature, is an essential part of this revolutionary research. The extraction process, spearheaded by Salah, begins with the selection of fresh spinach leaves. These leaves, nature's green powerhouse, are key to harnessing the powerful pigment, chlorophyll. Salah's keen eye for quality ensures that only the most vibrant and healthy leaves are chosen for the process. Once the spinach leaves are selected, they're introduced to a solution of 90% alcohol. This is a moment of chemistry magic as the alcohol starts to break down the leafy green barriers and the essence of chlorophyll begins to seep out, infusing the solution with its rich color and potential. The solution is then left to stand, allowing time for the chlorophyll to fully infuse the alcohol. This period of infusion is crucial as it ensures that the maximum amount of chlorophyll is extracted from the spinach leaves. Next, Salah employs careful filtration and separation techniques to isolate the chlorophyll from the rest of the spinach extract. This step requires a meticulous approach and a keen understanding of the chemical properties of chlorophyll. Through this process, the vibrant green pigments, rich in chlorophyll, are separated, resulting in a concentrated chlorophyll extract. But the extraction process doesn't stop there. The chlorophyll extract is then introduced to a polyvinyl alcohol solution. This creates a unique blend, a mixture of nature and science that forms the basis for innovative films with enhanced electrical properties. These films are the result of the intricate extraction process. But they are more than just a blend of spinach and polymer. They represent the potential for a new generation of materials, ones that harness the power of nature to advance our technological capabilities. The meticulous extraction process led by Salah results in vibrant chlorophyll-rich films ready for the next phase of experimentation. These films, born from the humble spinach leaf and transformed through careful chemistry, stand ready to explore the boundaries of material science and electrical performance. These films, a testament to nature's power and human innovation, are then exposed to gamma rays. This is where things truly get interesting. Gamma irradiation, a process that may sound straight out of a science fiction novel, is an essential step in the journey of these unique films. This form of irradiation uses gamma rays, highly energetic photons that are more potent than X-rays, to induce changes in the structure and properties of materials. When it comes to these chlorophyll-infused films, gamma irradiation is like the magic wand that brings their latent potential to life. Under the watchful eyes of Salah Lotfy and his team, the films are placed into an irradiation chamber, a device specifically designed to expose materials to controlled levels of gamma radiation. It's not just about zapping the films with a dose of energy, though. The process is a delicate dance of precision and control. The level of radiation, the duration, the rate, all these factors are meticulously regulated to achieve the desired outcome. As the gamma rays penetrate the films, they interact with the chlorophyll and polymer molecules. This interaction leads to the formation of free radicals, highly reactive particles that can trigger a cascade of chemical reactions. These reactions, in turn, alter the electrical properties of the films, enhancing their conductivity. But how does one measure such changes? Here's where Salah's expertise in material science truly shines. Using sophisticated analytical techniques such as X-ray diffraction, XRD, and Fourier transform infrared spectroscopy, FTIR, Salah and his team can decipher the structural changes taking place at the molecular level. XRD provides insights into the crystalline structure of the films, revealing any changes in the arrangement of atoms and molecules. FTIR, on the other hand, gives a snapshot of the chemical bonds within the material, highlighting any new bonds that may have formed during irradiation. Together, these techniques provide a comprehensive picture of the transformations occurring within the films, painting a picture of the intricate dance of atoms and molecules under the influence of gamma rays. But it's not just about understanding the changes, it's about harnessing them. By tweaking the irradiation parameters, Salah and his team can fine-tune the electrical properties of the films, unlocking unprecedented levels of conductivity. This isn't mere academic curiosity. The potential applications for such materials are vast and exciting. From flexible electronics to solar cells, the possibilities are as diverse as they are fascinating. The transformative power of gamma irradiation, under the careful watch of Salah and his team, unlocks unprecedented conductivity in these films. This is the beauty of science, taking elements from nature, combining them with human ingenuity, and creating something truly extraordinary. With the irradiation complete, Salah turns to advanced analytical techniques to understand the changes within the films. X-ray diffraction, or XRD, plays a significant role in his analytical toolkit. This technique allows Salah to scrutinize the films at a molecular level, revealing the arrangement of atoms within the material. What he uncovers is a dance of particles, a rearrangement of atoms brought about by gamma irradiation. But XRD is just the beginning. Salah also employs Fourier transform infrared spectroscopy, known as FTR. This technique decodes the various vibrations of the molecules within the films. Each vibration corresponds to a specific chemical bond, allowing Salah to map out the chemical landscape of the material post-irradiation. He finds that the gamma rays have transformed the chemical bonds in the films, creating a new, more conductive structure. These two techniques together, XRD and FTIR, provide a comprehensive view of the transformations within the films. They reveal a fascinating story of change, a tale of how nature's green power, harnessed through chlorophyll, can be manipulated to enhance the electrical properties of materials. This isn't a mere scientific curiosity, it's a revolution in material science. Salah's meticulous work demonstrates the potential of this chlorophyll-based film. Its enhanced electrical properties could find applications in diverse fields, from electronics to renewable energy technologies. Indeed, the innovations brought about by Salah and his team are a testament to the power of interdisciplinary research, combining the fields of chemistry, material science, and physics. Through their efforts, they've shown us that the future of materials might just be greener than we ever imagined. Salah's meticulous analysis reveals the secret behind the enhanced electrical properties of these innovative films. It is his unwavering dedication and expertise, combined with the collaborative efforts of his team, that have led to this exciting breakthrough. The story of this green revolution in material science is just beginning, and Salah Lotfy and his team are at the heart of it. Led by Salah Lotfy, this research is more than just an exploration of chlorophyll's potential. It's a revolutionary approach that blurs the line between nature and technology, opening up new vistas in the field of material science. By harnessing the power of chlorophyll, the team has created a novel, eco-friendly material with enhanced electrical properties. This could potentially revolutionize the electronics industry, paving the way for more sustainable and efficient devices. Moreover, this research extends beyond electronics. The potential applications are vast, spanning from renewable energy solutions to environmental conservation efforts. It's a striking example of how innovative thinking can lead to groundbreaking discoveries. This journey of extracting chlorophyll from humble spinach leaves, transforming it into an advanced material, and exploring its potential applications is not just about pushing the boundaries of science. It's about creating a sustainable future. The work of Salah Lotfy and his team at NCRRT is a testament to the power of innovation, paving the way for the future of materials engineering. What if the future of materials science could be influenced by a leafy green vegetable and a dose of radiation? Sounds bizarre, right? But hold on to your seats, because we're about to embark on a journey that merges the realms of biology, chemistry, and physics in an unprecedented way. Material science, The study of the properties and applications of materials of all types plays an integral role in our daily lives. It's the backbone of the technology we use, the buildings we live in, and even the clothes we wear. But today, we're going to focus on a unique facet of this expansive field, the world of polymers, specifically polyvinyl alcohol, or PVA for short. Now, imagine a team of researchers huddled together in a lab in Cairo, Egypt, their minds buzzing with the potential of what a simple plant component could do. Their mission? To enhance the electrical performance of PVA using an unlikely ally, chlorophyll. Yes, the very same chlorophyll that gives spinach and other green plants their vibrant hue. But the plot thickens. Their approach isn't limited to just doping PVA with chlorophyll. No, they go a step further by subjecting the chlorophyll-doped PVA films to gamma rays at varying doses. The goal, you ask? To amplify the electrical capabilities of this humble polymer even further. This groundbreaking work, published in a prestigious physics research journal back in 2008, promises to redefine the way we perceive the potential of everyday materials. It's a testament to the power of interdisciplinary research and the boundless possibilities it can unlock. As we delve into the details in the next scenes, prepare to view spinach and radiation in a whole new light. For what lies ahead is not just a tale of scientific discovery, but a glimpse into a future where the ordinary becomes extraordinary, where a leafy green vegetable and a dose of radiation may just hold the key to revolutionizing the world of materials science. Meet the explorers of this groundbreaking research: Rida M. Radwan, Salah Lotfy, and Omar S. Dasuki. Each one of them, a distinguished researcher from the Radiation Physics and Polymer Chemistry Departments at the National Center for Radiation Research and Technology in Cairo, Egypt. Together form a team that's as dynamic as the research they're conducting. Rida M. Radwan, the team leader, is a seasoned researcher with a wealth of experience in radiation physics. His expertise in the field provides the foundation for the team's experimental approach. Salah Lotfy, an expert in polymer chemistry, brings his innovative thinking to the table, contributing to the team's unique blend of disciplines. And lastly, Omar S. Dasuki, the team's radiation research specialist, whose keen eye for detail ensures that every aspect of their experiments is meticulously executed. Their mission: to push the boundaries of material science by enhancing the electrical performance of polyvinyl alcohol, a polymer known for its versatility, using a unique combination of chlorophyll doping and gamma irradiation. Chlorophyll, the very component that gives spinach and other green plants their vibrant hue, is the star player in their research. By integrating this naturally occurring compound into polyvinyl alcohol, the team aims to boost its electrical conductivity, but they don't stop there. They take this exploration a step further by subjecting the chlorophyll-doped PVA films to gamma rays. By varying the doses of this radiation, they aim to amplify the electrical capabilities of these films. This unique approach is a testament to their inventive spirit, a blend of biophysics and material science that's as fascinating as it sounds. Their work, published in Nuclear Instruments and Methods in Physics Research B in 2008, is a deep dive into the structural changes brought about by this unique combination. They scrutinize the crystalline and chemical alterations within the samples, unveiling a significant enhancement in electrical conductivity and dielectric properties. With such an ambitious endeavor, the results are bound to be electrifying. This team's mission is nothing short of revolutionary, promising a new pathway towards improving electrical properties for various applications in electronics and beyond. Let's dive deeper into the research process and understand how the team executed their mission. The team, a collaboration of minds from the Radiation Physics and Polymer Chemistry Departments, embarked on a scientific journey to push the boundaries of material science. Their unique approach involved the integration of chlorophyll, a key component found in spinach and other green plants, into polyvinyl alcohol or PVA. Their aim? To boost its electrical conductivity. But their approach didn't stop there. They subjected these chlorophyll-doped PVA films to gamma rays at varying doses, with the goal of further amplifying their electrical capabilities. In order to study the structural changes brought about by this unique combination, the team utilized XRD and FTIR techniques. XRD, or X-ray diffraction, is a powerful tool used to study crystalline structures, while FTIR, or Fourier transform infrared spectroscopy, allows for the analysis of chemical properties. With these techniques, they scrutinized the crystalline and chemical alterations occurring within the samples. The results were astounding. They unveiled a significant enhancement in electrical conductivity and dielectric properties. The team observed a dramatic 2 orders of magnitude increase in conductivity post-doping. That's like upgrading from a bicycle to a race car in terms of speed, but it didn't stop there. They also found a 15-fold boost in conductivity due to gamma irradiation exceeding 50 kilogray. That's like that race car sprouting wings and taking flight. This unique combination of chlorophyll doping and gamma irradiation had indeed worked wonders. It wasn't just an experiment, it was a breakthrough. It was a clear indication that the team's innovative approach was paying off and that they were on the right track. These results were more than just numbers. They were a testament to the team's hard work, dedication, and innovative thinking. They were a beacon of hope for future innovations in semiconducting polymers and polymeric capacitor production. The results revealed were nothing short of a scientific marvel. The team's findings were a testament to their hard work and innovative approach. What they discovered was nothing short of revolutionary. By integrating chlorophyll into polyvinyl alcohol, the team had managed to drastically enhance its electrical conductivity. But the magic didn't stop there. When they subjected these chlorophyll-doped PVA films to gamma rays, the electrical capabilities skyrocketed even further. Let's delve a little deeper into the numbers. Post-doping, the team observed a dramatic 2 order of magnitude increase in conductivity. That means the conductivity of the material was 100 times higher than it was before the chlorophyll was added. Imagine having a small light bulb and then suddenly having the power of 100 light bulbs. That's the kind of upgrade we're talking about here. But that's just the beginning. When they exposed the material to gamma rays, something even more extraordinary happened. The conductivity soared to 15 times its post-doping level when the irradiation exceeded 50 kilograys. That's like taking the power of those 100 light bulbs and multiplying it by 15. The team's in-depth research, published in Nuclear Instruments and Methods in Physics Research B in 2008, shed light on the structural changes brought about by this unique combination. Through XRD and FTIR techniques, they were able to scrutinize the crystalline and chemical alterations within the samples. The results were astounding. Not only did they observe a significant enhancement in electrical conductivity, but they also noted improved dielectric properties. This means that the material's ability to store electrical energy had also been greatly enhanced. The team's breakthrough work has opened up new horizons for the use of these materials in electronic applications. It's a giant leap forward in the field of semiconducting polymers and polymeric capacitor production. The future of material science looks brighter thanks to the innovative work of Reda M. Radwan, Salah Lotfy, and Omer S. Dasuki. These findings have potential to revolutionize the field of material science. The team's research doesn't just stop at these findings. It opens doors for future innovations. Their groundbreaking work isn't just a testament to their dedication and ingenuity. It's a beacon illuminating the path for the future of material science. Imagine a world where the electrical performance of materials is no longer a limiting factor in the advancement of technology. With this research, we're not just imagining, we're stepping into that world. By enhancing the electrical properties of polyvinyl alcohol using chlorophyll and gamma irradiation, the team is essentially rewriting the rules of material science. Let's consider semiconducting polymers. They're a crucial component in a multitude of electronic devices, from solar panels to flexible screens. Their conductivity, or ability to transmit electricity, determines their efficiency and performance. Now imagine if we could boost their conductivity by 2 orders of magnitude. That's a 100-fold increase. The implications are staggering. We could potentially see a leap in the efficiency of solar panels or the advent of next-generation flexible screens that are not just more resilient but also more efficient. And let's not forget about polymeric capacitors. These are the unsung heroes in our electronic devices, storing and releasing electrical energy as needed. A 15-fold increase in their dielectric properties or ability to store electrical energy could revolutionize how we design and build electronic devices. We could be looking at devices with longer battery lives, faster processing speeds, and more. These innovations are not just limited to the electronics industry. They could ripple out into sectors as diverse as renewable energy, healthcare, and even space exploration, transforming how we harness and use electricity. Yet this is just the beginning. The team's research has laid the groundwork for future innovations, setting the stage for further exploration and discovery. As we stand at the precipice of this scientific revolution, material science will never be the same again.